Okay, so welcome back to everyone who's here for part 2. So after talking with the people who are here in person, I realized that they think that if you just had the completed worksheet with you, but also the completed worksheet, but also the fill-in worksheet, it's much easier for you to go through and learn when you have everything there, but you can also see me code along. So in that case, if you do want the completed worksheet, I posted 2 links. One is to a GitHub link, a GitHub repo, and the other is to a Google Drive folder. For whatever reason, if your GitHub isn't working. So if you do want the completed versions, if you go to the GitHub or in the Google Drive, and within the folder, you'll see this scripts folder. And within that, wherever it says PHB RNA-seq part 1.rmd without the worksheet, that is the completed script. So you can go ahead and download part 1 and part 2 if you want. If you want to view the same within HTML, instead of in R, you can also do that. So download the HTML and view it. And that's what I showed you at the end of part 1, where I was showing you the density plots. So everything is over there. Again, it's totally up to you if you want to code along or just view it as I'm going through. But now that you have the completed worksheet, I'm hoping it should be a little bit easier. Sure. Okay. So within the Google Drive, we have the applied RNA-seq, which you should have access to, and then the scripts here, and then the PHB RNA-seq part 2.rmd file here, and the PHB RNA-seq part 1.rmd file here. And then the HTML is just over here and here. Okay. So let's start. Okay, so over here, I have the completed script open. You know that it's completed when it does not have the worksheet at the end, and I have this whole bunch of introductory text. So when you do go through the completed worksheet, you'll see that I have tried to detail every single function as much as possible. So you can just follow through with there, or you can work along with me over here. Then, yep, okay. So just loading in our packages here. And then this should also be ready for you. Okay, so just a little bit that I wanted to talk about our normalized data. Now, this is RLE normalized and CPM transformed. Now, when you are on any public repository or like websites such as Geo, you usually have an option of downloading raw data, which has not been processed at all, or you have processed data. And the way that people label these are just up to them. Like, you know, there's no standard naming convention. But as a general rule, when you are at that stage that you want to submit data, I would always say to upload your raw data files and let the people who download it process it by their own processing pipeline. Because when you're downloading processed data, again, like we see, the workflow that we're applying here doesn't necessarily mean that the other person is going to apply the same thing. So it's you can always provide your processed data, but it's where like always appreciated when you upload your raw data, because I do see a lot of entries where it's just processed data and I'm like, I don't know what you did, or the methods that you use are not methods I would use, so I don't trust the way that you've done it. And so when you have the raw data, it's much easier to compare it against whichever data that you want to. Okay, so that's just some advice I would like to give. Okay, so going back to our worksheet. So I'll be working through the worksheet, but like I said, everything is over here. If you want, you can just like copy paste all of this into the worksheet as you're going through. So we'll start with the first thing first step, usually with process data, which I like to apply, is called as principal component analysis. Now, again, I won't be going through what it means, but it's basically reducing your data down to smaller data points so that you can view the variation in your data set as a whole, just within your samples instead of visualizing each and every single gene. So we'll start off with first converting our log2, our enorm matrix. No, so we'll call this E log2. So as we did in our previous part 1, we want to make sure that we transform it to a x+1 transformation instead of just the log2. So log2 E norm plus 1. Okay. So that's our transform to log2. And again, you can do log 10 as well. It's totally dependent on you. But I realized when I've worked with log 2 versus log 10 just very recently that log 2 gives you a much finer resolution of your data than log 10, where log 10 condenses down the values a little bit too much in my preference. But again, if you have gene expression values which are very, very high, log 10 works. Then we're going to do a function called as transposing, which means that we're going to convert the rows into columns and columns into rows. Now you can do this. There is a dplyr or tidyverse way of doing it. I think it's just the transpose function, but this is what I've been using for a very long time, but it does the same thing. So we do T, which stands for transpose, and then the name of the data frame. Do not open this data frame because when you have columns with more columns than you have rows, it crashes R. So it might take a long time for R to start again. If you want to just look at it, you can type in the console T. Oh, even this might cause a problem. Yeah, so this is how it works. It's a really big data frame. So don't open it. It's just converted your rows to columns, columns to rows. And then just to check that you have everything in order, just look at the dimensions, that. And we get, yeah, so we have 126 rows and 11,860 columns, which is the same number of genes that we started with in our enorm data frame. And so the actual function to run PCA, I'm just going to name the object as PCA, is prcom. We use the transpose data frame because this prcom function works column-wise, and because we're wanting to see the variations between our genes, which are first present as rows, we transpose it so that we can get the variation within each of the genes instead of within each of the samples. Okay, that's why we use the transpose one. Scale is false because we have already normalized. So this is normalized data. That's what it stands for. And center, I put it as true, which means that it actually converts it into a Z distribution score. So you have it converts all the values into standard deviation values so that you have a 0 value as your center value and everything spanning off from that distribution there. Run that. Okay, and then you, just to see what the object looks like, you do summary PCA. And this is what you'll see. So over here, what we're seeing is principal component 1 is contributing to 0.34, meaning 34% if you multiply by 100 of the variance that we see within our data set. And then PC2 is contributing 20% of the variance, going to a cumulative of 34 plus 20, giving a 54% variance. So each single principal component is going to be the first principal component is always showing the highest variation, and all the progressive ones decrease in the amount of variation that they contribute. And then obviously you can imagine at the end, the cumulative proportion is going to be 100% because each of our principal components will add up to 100. The number of samples you have is the number of principal components that you will have. So we have 126 samples. So this will go on till 126 PCs. Okay, so we got that. We have that in text form. Now, if you want to visualize it, this is a very simple base R function just to view that. It's called a scree plot. And that's how you see the distribution of your PCs. Now, it's okay. It shows us the basic thing. PC1 is having the highest variance, PC2 lower, and then you kind of get a tail around here. So this is kind of where here or here we start to plateau off. So that's where I see okay, I would say that PC1, 2, 3, 4, 5, 6, 7, up until PC7 is when I see the most variation within our samples after it tapers off or plateaus. So I won't consider those PCs for my analysis further down if I wanted to include my principal components. Now, I don't really like how this plot looks, so I'm going to make my own. So you already have the code over here. If you just run that, we are making a separate data frame that shows that we want a column called PC, which has numbers from 1 to 126. Variance explained is the standard deviation of our PCA. So within our within our standard deviation object. So this is the PCA standard deviation values that we have. So it's just saying to apply these formulas to get our variance explained, our cumulative variance, just to basically represent what we saw in text form into a table form. And then cumulative percentage is just multiplying the cumulative sum that we have by 100. So basically, this is what it should look like. So what we had exactly in the summary PCA is what we kind of get in this data frame over here. And now, if we want to plot that, and like I said, you decide on the number of PCs to consider. For the purposes of this, I'll just take the first 30 PCs, okay? So just rewriting summary as from row number 1 to row number 30. So we only get these 30. And if I run this, this is what you get. So it's exactly the same scree plot, but just in a much better format. So we see that the variance explained over here is what we were looking at, about 34. You can again change the y-axis to percentage axis if you want. Now, if you wanted to do it by just a dot plot, that's also something you can do. So it's just different ways of visualizing the same data. You can do the same for the cumulative. So if I just put in cumulative perk here, run that. So it just shows and this will eventually reach 100, but we only have 30. So, and we see it's about right here. Okay. So then that's basically how we would visualize what our principal components look like. And for that, we'll go on to actually store the scores that we get as a separate data frame, because we will be using that later on. So when you look at the actual PCA object, there's this X value, which contains all of the scores. And then if you open the scores, this is what you get. This is the actual principal component values for each single sample and each single PC. Okay, so we have that. And then now we have these two data frames called as EDAT and PDAT, so our expression data frame and a phenotypic data frame. There's another type of data frame that I use or I've been taught to use, which is called the metadata frame. So metadata is basically all of your data, which is not your, which is how I think about it, which is not just your clinical data. Now, this PC data that we got is not phenotypic or clinical data, but it is data that we want to attach to our samples. So we store that in a data frame called as MDAT. So metadata. I use the very crude command of cbind, which is column bind, because I know that scores is C1 to C126 in order. And I know also that PDAT is also C1 to C126 in order. But you can use inner join, left join, right join from tidyverse to do the same thing. But because we already know, I'm just going to use cbind PDAT and scores. So if you open up MDAT now, this is what you see. So we have all of our PDAT values, but now we also have our PC1 to 30 values. Okay, so we have all of that stored. Again, to mention, all our samples are as row names over here. Okay, so we have our MDAT ready. Now we're going to do a correlation to check which of our variables, like all of our variables within PDAT, are actually contributing to the variation that we see in our data. Okay, so we're going to use a package called a PL-omics package. This was actually written by Victor Yuan, now Dr. Victor Yuan from the Robinson lab. And he's made it very easy to run this function. So I have so if this is not running, so you would have to install the PL-omics package. So just uncomment all of this. The way you uncomment everything together is Command or Control Shift C. Someone told me that if I explain the shortcuts I'm using, it's much easier. So if you just do Command or Control Shift C, you just uncomment or comment everything together and then run the whole thing. So you'll be able to install PL-omics. Okay, so we've loaded that. And then we have, I'm going to name this object as variable variance. You can name it whatever you want, but I just wanted to make it as explicit as possible. LM matrix is the function we're using. Dependent is the dependent values that we're going to be using, which are our PCA scores. Independent are our variables that we want to see the effects by, so PDAT. So you can either have a different data frame with only the variables that you want, but over here again, I'm just going to select columns 2 to 15. So that would be columns 2, so that's age, to 15. So basically just taking out the first column. So if you just hover over that, you can see it's column 15. And then the metric that I'm going to use is p-value. So I want to get the output that I want is the p-value or the probability value of which variable. So like what is the probability of correlation of this variable with the PCA scores that we're seeing. So if you run that, okay, it's not working. Oh, okay, so this needs to be in brackets. That should work. Perfect. So you get something that looks like this. Okay, so it's a long format data frame, but basically for each PC, we see how much that variable is contributing towards our entire data set. Now I'm just going to we're going to just manipulate the data a little bit so that it's easier for us to put it into a plot. And I think it's basically all of this. Let me check. Okay, yes. So if you just run the whole thing here, so we're converting it to a data frame. We're calling it VVplot as data frame. Now then we're transposing the data frame. So again, rows to columns, columns to rows. So that's what it will look like. So now we have everything in a bit of a tighter format. You know, this format makes sense to us because we have all of our samples as rows and then all of our variables as columns. And then I'm going to add a column called as principal component and have the input as numbers 1 to 30, and then select the principal component column to be first, and then the rest of the columns. Okay. Mm-hmm. Hmm. Oh, okay. I think it's running for you. Okay.
You skipped a command scores.
Oh, I didn't. Okay, yes. Thank you for pointing that out. Okay, so scores. Oh yeah. Okay.
Scores C1 to 30.
Yeah, so that, yeah, so basically just selecting only the first 30. Yes. 30. Okay, so now that should work. Okay. No. Sorry? I think so. Okay, maybe I'll just, okay, I'll just slice this up because it should have done that before, but. Okay, so it should work now. Yeah, okay, so what I basically did is just take the first 30 because I had 126 rows. When I wanted to add just 1 to 30, it wouldn't work because it's like the rest of the rows are empty and R doesn't know how to deal with that. So I just basically, where I select the first 30 columns, I selected the first 30 rows. And then pivot longer as we've done before. So this is now what it would look like. Principal component 1 for each single variable with the p-value here. And then we're going to add another category. So this is a p-value category, which oversimplifies the p-values that we have. So we have, if it's more than 0.05, we'll have it more than 0.05. Between 0.05 and 0.01 as less than 0.05. Between 0.01 and 0.001, we have less than 0.01, and then less than 0.001. So it really delineates the p-values that we have. You cannot do that. That's completely up to you. But I would like to get a little bit of a better resolution in what we're seeing. And then if you run that, that is how it looks. Again, it does not look great. It's very difficult to see through. So I have a couple of extra commands. So we're going to give assign colors to each of the variables that we have within our p-values, and then have the principal component as a factor so that it's easier to plot it, and then have it store it within a object and then run the object here. So this is what you should get. And what this is showing us is that from PCs 1 to 30, because over here okay, no, okay, so we see that the ones which have a p-value of more than 0.05 are just colored white, so we know to ignore them. But anything less than that is colored sequentially, and the darker the color, the less the p-value, meaning the more significant it seems to be. And so we see there's quite a few. So we see that the score Apache 2, I don't know how to pronounce that. COVID also seems to be contributing very highly, as well as ICU, mechanical ventilation, but basically all the ones which have orange in them, meaning that they're having a p-value of less than 0.05. And if that is your p-value cut off, then those are the significant variables. So then I have a little bit of an assignment here. So what I'm asking you to do, so over here where we asked you to put in p-value as the metric, you can also put in r squared, r squared as the metric over here, and follow the same things. And instead of using scale fill manual for the plot, you use scale fill gradient as white, and then like high versus low for white versus orange. So I'll give you like 3 minutes to do this because it's basically the whole thing just copy pasted. You can take a look at the filled worksheet because it's right there. Okay, now because I do have the part 2 open right here, what I'm going to also do is just copy paste, but I'll explain what everything means so that we can run through this in time. Okay, so I'm just going to name the object r square. Again, LM matrix, the dependent as scores, independent as the same variables in PDAT, and the metric as r square. So we do the same thing over here, convert it to a data frame, and then transpose it over here. So the way I'm just running a single line of code is wherever I want to run the code for that line, I keep the cursor there. Command or Control Shift Enter will run just that one line of code. Or again, if you just want to run just this part of your like command, then just highlight it and then Command Shift Enter again. So that's the shortcut. Okay, so did that. And then this is how our r squared looks like. So again, it's basically in the same format, but now the metric is r squared. So we pivot longer, again, as factors, so that when I put principal component as factors, it makes sure to list it from 1 to 30 instead of just 1, 11, and then 2 and 20 or whatever. So it goes in it sequentially. And then we see, we're just going to look. So the stir function just gives us, again, like I showed before, how our variables are looking like. So we have character and we have numeric. And then we're going to store this in a separate object. So over here, everything was the same, but I just change the scale fill gradient because now we have a continuous scale, and R squared square is a continuous scale, as if you've used this metric before, you would know. And now I'm just going to put those two plots together, and this is what we see. So it's always good to have a p-value, but also the R squared just shows you the strength of the correlation that you have as well. So even within that, we see that, okay, our R squared isn't great. I know it only ranges from, like, let's say to 0.3, but even in that, we can see that mechanical ventilation seems to be contributing the most or having the highest correlation within PC1. And over here, we can definitely see that it is also significant by its p-value. And then we also see, like within PC2, we have quite a few which are strongly correlated. So this just gives you another dimension of looking at the data and the variables that are contributing towards the expression that you see within your data set. Okay, so moving from there, now you've seen all of these PCA plots. How do you actually make them? It's actually very easy. So given that we have stored all of our principal components within our MDAT data frame, I'm just going to use that. And then plot aesthetics, X is equal to PC1, Y is equal to PC2. Now over here, I would, like, people can generally just write PC1, PC2 without the X and the Y, but just good and like best practices in code, make your code as explicit as possible because it helps you remember. And when you're sharing, you don't have to go back and annotate everything. So if it says X and Y, just put in X and Y. It will be much easier for you later on, I promise. And then color, we're going to color it by COVID. So let's see how our samples separate by patients having COVID and not having COVID. Then genome point, so scatter plot, and I'm going to specify the size of the plot as 3. Labels. Again, we're going to add the scale color manual so that we have the gray and the orange for the dots that we're going to see. Team has minimal because it's just easier to view. And then when you run this, this is what you should see. And it doesn't look like a sample separate by COVID status, which means that COVID doesn't seem to be a variable that drives a significant amount of expression difference within your data set. So, I mean, looking at the question, whatever result you're getting, it depends upon the questions you're asking, whether it's a good result for you or not such a good result or what you were expecting. But again, there are no right or wrong answers. It's just what it is and the questions that you ask of the data. Now, one thing that has again been taught to me by a previous lab member, Dr. Julia Del Gobo, who's now in Ontario, but she said that when we look at this, you'll see that the y-axis and the x-axis are actually different. So the either ends, you can see that maybe it goes up to 150 positive, but only a negative 100. And when you see this, you think that, okay, this is the distribution of the data, but it's not represented in the correct axis. And because of that, you might have a different interpretation of the data than what it might be. So what we're going to do is go back over here, add an additional function called core Cartesian, which allows you to actually set the limits of your axis. And I'm going to go for minus 130 and positive 130 for X, as well as for Y. Now, this is a step that a lot of people eliminate, but I think it makes it very clear as to how your distribution falls and how your samples segregate if you just add this one step to make all the axes the same. So now you can see like it's the same plot, but it might be visualized a little different. Yes.
Sorry, since that command is not
Uh-huh. Yes. It's right here. There's different ways of doing this as well. Like you can set it using a different argument, but this is the one I like to use. Did that work? Okay, perfect. So then I have all within the worksheet, I have a few more sections where you can do the same thing for each of the different variables. Now, given that PC1 and PC2, the X and Y axis limits are going to be the same. So the plot is going to look the same because it's the same principal component values, but the variables that you're actually using to annotate them are going to be different. So all you need to do, and I'm only going to show one example, is you just copy paste that here, change this to ICU, and then whichever color you want. So I have gray and blue. Just change the colors to whatever you want. So it's the exact same plot, but it just shows us the separation by the variable of interest. And you can do this for PC2 versus PC3 for however you want, for whichever variable that you want. Okay, is everything clear so far for principal component analysis? Everyone on Zoom doing okay? I'm going to take that as a sign that everything's going well. So now we're going to turn into differential expression analysis. So we're going to use the package called as Lemma, which again was built for RNA-seq analysis. You can also use the DE-seq2 or the EDGER packages. They also have their own methodologies of using it. But Lemma has just been used in our lab, and like comparing to DE-seq2 and EDGER, it returns less false positives. However, there was a paper that was out recently, and I think it's very important to mention that when the authors of that paper actually compared all of these different tests, specifically for RNA-seq data for differential expression, they actually found out that the very simple standard non-parametric test, which is a Wilcoxon rank sum test, actually perform much better than Lemma or DE-seq2 or EDGER. That is something I still have to personally check, but so far I've been using Lemma and it's been working okay. But if you do want that, I can add that paper to the repo as well, because I think if you're doing this sort of analysis, it is very important to have a look at what is going around and how methods are constantly updating and the discussion surrounding them. Because when people ask you why you use this method, you need to have a answer that is backed up by your literature search as well as your actual computation. And so I will be adding that paper. But for this workshop, we're just gonna keep on working through them. That doesn't mean anything else is wrong. It just means one might perform better than the other. Okay. So for like differential expression analysis, we first need to select the variables that we want to input into a differential expression matrix. Now, we have so many variables over here. We have 15 variables. So we can realistically put in all 15, because the more variables you feed into your model, the less reliant it becomes, and it starts overestimating or underestimating the expression contribution of the genes that you see in your data set. So we're going to select some variables that from our p-value and r-squared analysis, we found that to be most significant. We're going to build a model matrix, which is the second step that we do. And then we're going to apply Bayesian statistics. Now, okay, I still have a few stickers. Let's see who can tell me what Bayesian statistics is, just very, very simply. It's okay if it's wrong. No, that comes later. Okay, so Bayesian statistics basically means that it uses something called as prior probability and posterior probability. Now, this is the step that we're going to be applying. I'll show that when we go through, but basically it's a heavily debated topic whether you should apply Bayesian statistics or not, which means that it takes into account the whatever transformation you've done with your data, and that is something called as prior probability, and it applies that little bit of learned knowledge to the actual model and function that we're running. So some people don't like using this prior probability and updating your model that you're going to be building. Some people like prefer it. So again, Lima does say in their manual that you should be applying this. And so that's what we're going to do. And so the steps to follow this is that we first make our matrix. Let's call it COVID. So the function is model matrix. So we want our explanatory variable to be COVID. And then our p.data frame. And then this is how it looks like. So what we're saying is within our p.data frame, only take the COVID column, and then so it automatically, the model matrix function automatically turns the column name into a very specific one called as COVID yes, which means that if there is a 1 over here, that means that sample is indeed a COVID patient. If it is 0, that means the sample is not, like the patient does not have COVID. And then the intercept is just a control, like I wouldn't say control, just a baseline variable that you do put in, just like the log to x plus 1, the plus 1 that we use. So I would always encourage having the intercept. People do remove it, but I just keep it in there. And then we move on to, again, checking that all our column names match our row names. True, so that's good. This is very important. And then we run the actual model. So I'm going to call the model efit COVID. And the function is lmfit. So we're fitting the model to our enorm data frame using the COVID matrix. So this is only taking into account the COVID variable, none of the other variables. Okay, so then this is kind of what it looks like. There's a lot of measurements in there. And the the Bayesian statistics that I was talking about is a function called as eBayes. So you just do that, rewrite the data frame. And again, it's going to be the same, but it's added a few more variables to the data frame. Not the data frame, sorry, the array. And then, so these methods, these arguments that I've written over here are just a way to pull out the results of our differentially expressed analysis. Now over here, the function that we use is called a top table function. We put in our efit COVID object here. The coefficient, when the way you get the name of the coefficient is actually you go within your COVID model matrix and then look at the name of the column over here. So the COVID yes. So what that means is I want the function top table to pull out the differentially expressed genes by the coefficient COVID. If you have multiple, which we will have in the later steps, you then need the coefficient then becomes a very important argument, because then there are several columns that you could choose from. But here we're saying to choose a COVID yes column. Adjust method. Now this is multiple testing correction. Okay, can anyone explain multiple testing correction? Yes, Zoe?
Would that just be like, if you were to say on a threshold of like 0.05 or 5 error, if you see that again.
Yes. Exactly. Yes. So multiple testing deals with when we have lots of different tests that we're doing. So then when we keep on doing those kinds of tests, we have a lot of tests that we're applying to a single data set. Now, in order to adjust for those number of tests, we do something called as multiple testing correction. And then there are different methods that you could use. So this is the false discovery rate, or called the Benjamini-Hochberg method. Or you can use the Bonferroni method, which is a bit more stringent. And the way, like, the statistics of these are a little bit different. They rank by the p-value, and then anything above or below that p-value is significant or not. So you can go and read about that in your own time. And so given that the FDR, or the false discovery rate, or also called the Benjamini-Hochberg, is a little less stringent than the Bonferroni, that's the one that we're going to use. And we're going to set the multiple testing parameter, not the p-value threshold. Like, it's called p-value, but it's the multiple testing p-value to 0.05. Okay, so then when I run that, it only shows me the top 10 differentially expressed genes. And these are basically like the columns that you get. So you get a log fold change, your average expression across all the samples for that gene, a t-value statistic, so the t-test, a p-value, which is your original p-value, the adjusted p-value, which is after multiple testing correction, and a beta value over here. And so I don't know why I have this again, but I'm just going to, you can also sort your data frame by either the p-value or the log fold change. So what I'm going to do is just sort by log fold change, and it shows me that the S100A9 gene has the biggest log change difference between patients with COVID and patients not having COVID. And this is the adjusted p-value that we have. And given that we've already said a p-value of 0.05, anything that is not significant is not being shown in this table anyway. So, yes.
So, molecular biologists like to normalize qPCR data, like to pick a housekeeping.
Yes.
We assume that housekeeping genes don't change. And here, it looks like you've got a negative 4,400 log fold change on beta actin, which is the most commonly used housekeeping.
Okay.
Any idea on what's going on there?
No idea. I could go back in the paper and look at if they actually did this validation for these housekeeping genes. But yeah, it shouldn't be showing up if it's a housekeeping gene.
Is that p-value in that?
Yeah. No. Okay. Might be something with the data set. I don't, or something. Yes. Okay, well, so you can see, like, every single step we apply is so important over here that it can drastically change the results that we see. So maybe the normal, like the processing method that they use is going to be a little bit different, and maybe they didn't pull out these genes. But that's, again, it depends on how you analyze your data. Nothing is wrong, like right or wrong, is just as long as you have backing and I won't say proof, but validation of why you're using certain steps, and you can defend the results and the data that you have. That's basically, I think, how it goes in data analysis.
Average expression in each group? Just the average.
I think just average across all samples. Yeah. Okay, so now that we have that, and then we see, okay, so if I do it by p-value, we get GBGT1. So this is the most significant gene by p-value, and S100A9 is most significant by log fold change. And now I just want you all to just take a minute and Google S100A9, GBGT1, and COVID, and see if there has been any literature so far, besides this paper, that might not have even gotten these results because of their different processing pipeline. If there's anything to speak between the correlation of these three.
Pull those rows, I can see that. Active data.
Let's see. Oh, I haven't loaded an EDAT. I'll check that later. Okay, anyone found any correlation between these three, the two genes and COVID? Yes, Zoe?
Yeah, I just saw that.
Okay. So that Zoe just mentioned that she saw that S100A9 does come up as being more severe in COVID patients with having higher expression. So just off the bat, it seems like we might be going in the right direction, but when we're looking at COVID patients versus non-COVID patients. Does that kind of make sense? Okay, cool. So then it took me a while to find this out, but basically, given that top table only shows you the top 10 results, if you want to save everything to a data frame, all your results, and you want all of them, you just put in the n is equal to infinity, and it gives you all of the results at those specified parameters. So adjust a p-value of 0.05, and then you can pull out and work with this however you want. Okay, so okay, so another thing was like we saw that if we go up over here, that if you look at age does not seem to be contributing anything towards like the expression we see in our data set. But we did see within our exploratory data analysis that patients which have higher age seem to have COVID. So let's see if putting age in the model actually changes anything in the results that we see. Given we would expect it not to, given that it's not showing up in any of the statistical tests. And we only saw that by visualization that age seemed to be contributing. So we're going to do the same thing here. Make a model matrix, MMH. So over here now, I'm going to specify age as a variable to be controlled for. And then now we get two columns here, COVID yes versus age. And okay, in the field worksheet, I do a logistic regression, but I'm going to skip that because I'll be coming to that later on in this COVID age lactate as well. And then we just follow the same functions as before. Now let's see. Okay, so it looks like it's S100A9 is still the top differentially expressed gene by log FC, and GBGT1 is also the top differentially expressed gene by p-value. So it looks like including age in our model matrix actually does not change the results. You will see, however, so if I do it for this one, you will see that the p-value might change a little bit, and it has. And that makes sense because we did include an additional variable in our model. But this example was just to show that if you are including variables in your model that you know from your previous analysis don't actually contribute towards the model, they might change the expression a little bit, but they don't seem to be contributing to the overall output of the model. And in this case, when you do see that they're not contributing in the earlier steps, just don't put them in the model, because it's just you're adding an additional parameter that is not needed, and you can skip that. Because as I said, the more variables you add, the more information you're giving the model, which can lead to over or underestimation. So now I've just chosen lactate as an example, because if you scroll up, you'll see that for principal component 2, we see that lactate is contributing a little bit towards PC2 at a significant p-value of less than 0.001. And it also shows up a little in our R-squared, not heavy correlation, but just an example. So what I'm going to do here is, again, just run through the same functions. Now I'm doing these reiterations just to show you how the model changes over time according to the variables that you add. So it's very important to take be conscious of the variables that actually go into your model. Just gonna add. And then I'm going to do the logistic regression model that I mentioned before. And the reason that I'm doing logistic regression is because we have a continuous variable on one hand, which is lactate, and then COVID, which is a binary variable. So the test to compare them is logistic regression and not linear regression. So over here, I'm going to use the GLM function, and then COVID, yes. So we are going to be using the model matrix. So the column is called COVID, yes, versus this variable here. Data we specify is our model matrix, but in a data frame format, and the family is binomial, which is how you specify it is actually a logistic regression. Okay, so that's what you get. This is kind of the output. And if you just do summary, this is the actual output of the model that you're getting. So it shows us that, okay, lactate, so you can just ignore the intercept, but the lactate actually seems to be contributing quite significantly to our data set. And then the rest of this, you can go and check what these other parameters mean, but I'm just going to look at the p-value over here and be like, okay, seems to be quite significantly affecting the variation in the data that we see. And so if you just run this here, this is just the visualization of the model that we built. And it shows that, okay, it seems like people who actually do have COVID, so you can see the probability of positive COVID status. So 1 being having COVID and 0 being no COVID, that people with COVID seem to have a higher lactate concentration than the ones who don't have COVID. This is not like the best way to visualize this, but still it gives us a rough estimate of that, okay, lactate concentration does seem to be a variable influencing our expression data. So then, yes.
Sorry, so in this example, you also included age.
Yes, I did. Yes. So I should have, so you can definitely just take it out. We can do it without that. Actually, yes, I don't know why I had it. I think it's just because I was just running through the examples and we know age doesn't affect it, but we can very well just take it out.
Does that reflect in the plot?
Let's see. So I just removed that. It doesn't, because that's exactly what we saw, right? In the previous example, it doesn't seem to be contributing to the expression that we see. So, okay, so now I'm just going to, so yeah, basically, if you want to do the fit again, you do the same exact steps as before over here. And that is the model that I will basically use further on. So these are just like, again, I'm showing like quality checks that you would use to choose which variables to get within your model. And so I'll just do efit lactate LM-FIT genome, and then when we pull these out, now it is not S100A9 that's the top most differentially expressed gene by log fold chains. It's actually HBA2, and it has a much lower fold change if you compare with the S100A9. So this variable does indeed change the results that we see. And so that's what I mean. Like, you have to be careful again when you're selecting which variables to include in your model, because if you did include, the results you're getting are different. But if we check by p-value, it doesn't seem to change. But then again, when we are talking about biological data, a log fold change value is much like, once you have everything that is significant, a log fold change value actually shows you how much of a difference there is between the genes that we see, right? So that is the metric that I use more, like once I have everything subset by my p-value that I want. Okay, so this, I think you can just probably run. Okay, so basically this was just an example to show that since we did get S100A9 as the top differential expressed gene without lactate, is there indeed a difference that we see visually? Because statistically, we are getting a difference. Now, it looks like when we actually, so what I've used is, I've just converted everything into log2 within eNorm, pulled out just the S100A9 gene, and subset by COVID patients and non-COVID patients. And it looks like, yes, so patients who do have COVID, seems that their levels of S100A9 seem to be lower. And while it might not look as much of a difference visually, we do have a statistical test that confirms that. So I would rely more on the test than the visualization that we do see over here. Okay, so then it's the same for HBA2. So I just left this over here so you can fill it out for GBGT1 and HBA2 just to see how much of a difference there is or is not visually. And then so I'm just going to skip that. Okay, and so now there's actually, I think we're running quite ahead of time, but that's good.
Could you go back to the top table? So it's looking at just S100.
Yes. So that would be here.
So long fold change is not.
What do you mean?
So you're saying that it's a minus 10,000 log fold change?
Between COVID, yes, and COVID, no. There are sometimes I do get these like really high values sometimes.
Yeah, but a fold change is a ratio.
Yes.
So a log fold change is just the transform of that ratio. So a log 2 fold change of minus 10,000 is like a fold change of log.
Yeah.
But if you look at the actual data, the fold change is not that different.
The actual plots, right? Yeah, I know.
So I think there's an error in the labeling of that log fold change.
Okay.
I don't know where it happened, but like if I was to look at log fold change here, I would
Yeah.
say maybe, 1.1 fold change, 1.2 fold change. So as a log, it's going to come off as even smaller,
Yeah.
but not minus 10,000.
Mm.
So I don't know what happened.
That is okay. Yeah, you make a very valid point.
Typical log 2 fold change, you're looking for somewhat centered on 0.
Yeah.
Right, hovering around the log 2 fold change of 1 is 2-fold different. Right, so if that was 2-fold different in your average expression, then you'd expect one at 15 and the other at 30.
Okay, I think I've seen this sometimes happen when there are like really big outliers, as we can see over here. That does influence it a bit. So it might just be that, because I do sometimes see genes which have like quite a few are within like a good average range, but then just these outliers just drive that a lot. But then in that case, then you'd have to go back and take those out and then rerun the model again. Yeah. Okay. Any more questions on Zoom? Okay, cool.
Actually, sorry,
So-
Nikita, there is one question on Zoom. It is, wouldn't you clean data of outliers before running analyses?
Yes, you would. Sometimes, however, it is a reiterative process. So sometimes you only come across these outliers when you're actually visualizing the data later on. So in this case, then you would go back to your raw data or your normalized data. Actually, again, it depends. Remove those outliers, but that means that you're also be removing a lot of like other data, because it might not just be this one gene, right? There might be several genes that are showing like such high outliers. That means you're reducing your data as well. But that is definitely something you can do. The only thing is, like, once you do that, I would say you would have to normalize again, because if you're just doing it on the raw counts, that's fine. You can follow the normalization method. But if you're actually subsetting within the normalized data set, that means you're removing a lot of data within your normalized data. And that data set is then not scaled, it's not centered to what the original normalized data was, because normalization actually takes into account every single gene within every single sample and then gives you that numeric value either to be added or subtracted. So if you do remove these outliers, which you definitely can, or there's basically, you can very clearly state that we do have outliers, and so this data might not, there might be still a lot to say about this data when you want to like go forward, publish, or just present it. If you do, remove those outliers within your normalized data set, then you have to normalize it again. But also, that might also be cherry picking. So you need to kind of, I don't know, have a discussion about this with your own lab group, or just the people that you're doing this analysis with, because if you just selectively start to remove outliers, then that is not actually the true representation of your data. But also, again, coming back to removing it, in single cell RNA-seq, that is actually what you do a lot. You go in, you look at your data, you visualize it, you find out not exactly outliers, but things you need to control for. You go back again, you do the whole process. So it's a very reiterative process. So it really depends on the type of data you have. And again, are you verging on selective, on just like selecting genes just to benefit the expression and the results that you see? Did that answer that? I know that was long.
I think so. There's nothing else in the chat for now. Thank you.
Okay, thanks, Amy. Okay, so cool. So we'll head forward from there. So you can do this on your own, the HbA GBGT1. And this whole code chunk that we have over here is pre-written and you can run it. But sorry, I'm going to explain this step by step. Now, this is basically for when you have time point variables, meaning that you have a day 0, day 1, day 4, day 16, whatever, and you want to compare these time points and see the differentially expressed genes between these time points. Because our COVID data set did not contain them, I made a dummy variable, which is just going to show us how to use that function, but it does not give us any results because it is a fake variable and is not tied to any expression within our data set. So I have called this dummy variable unicorn. Okay, so then we're going to make a unicorn COVID data frame. And what I'm going to do is just put in some random numbers generated within our unicorn data frame, which says that the expression of the unicorn protein at 0 days was this much. At 7 days was this, and then 14 days was that. And then basically I'm like reducing the expression as I go from 0 to 14 days. And this is kind of what your data set with time points might look like. And then I'm just going to select, and these are only the ones which have COVID. And so this is unicorn non-COVID because I have to make it separately. And then unicorn non-COVID is going to be exactly the same. Like if you don't have COVID, the unicorn protein is not going to change. So that is what unicorn non-COVID is doing over here. It's just within a certain range at the same exact inputs. And then I'm just going to bind that to form a PDAT unicorn, which has all of our unicorn measurements. Yes, for COVID patients versus non-COVID patients. I'm just going to select everything. I'm going to remove the COVID column and just have our measurements and our samples as we did in our PDAT. I am going to right join. So I'm going to keep my PDAT unicorn data frame as is, and then I'm going to join it to our PDAT data frame to have so I just added it to our PDAT over here. So we have 0, 7, and 14. Okay. And then I'm just selecting only the actual columns that I want. So sample, COVID, unicorn 0, 7, and 14. I am going to make it a longer data frame as we have done before. So days is unicorn 0, like the number of days and the measurement. And then just re-level so that I always get 0 days as the first variable with, and then 7 and then 14, easier for plotting. And so this is how it should look like. So this is basically like simulating if there was a unicorn protein at time points, which reduced from contracting COVID at 0 days versus 14 days, like after 14 days of contracting COVID. And then we're just going to use the same exact function as we did before, the model matrix for COVID. But in this case, we're going to include the actual, like, no. Okay, I'm going to make the model matrix to include 0 days, 7 days, and 14 days with from our PDAT. That's how it's going to look. It's the same exact format. And if I run the model, we're going to see there's like no significance, but because of course the unicorn protein does not exist and is not tied to any gene expression within our data set. However, what changes is now this part over here. Now we do the LM fit. So the enorm versus the unicorn model matrix, but okay. While that's running, so what I do is over here, I use the make contrast function, which specifically I want to tell the model that I want to look for differences between unicorn 14 days versus 7 days, 7 days and 0 days, and 14 days versus 0 days. You'll know that over here, I did not run the eBase function yet. So when I do this matrix, this is what you get. So again, it's a 0. So over here, what it shows is that it codes it by if it's present at 0, like if it's not present at 0 days between, no, sorry. If the sample, no, how do I explain this? It basically gives you a measurement of whether the unicorn protein is present at day 14 versus day 7 when comparing to actually the protein, the PDAT data frame that we have. And when you have specified the levels of unicorn here, so remember that this is our actual model matrix. So you're fitting your contrast matrix to the actual model matrix that you made before. Now we'll check. So we have actually converted the row names of our conmat over here to the column names of our actual model matrix, just so that it's easier for us to work with. And then I do, instead of using the LM fit function now, I use the contrasts fit, but I use the LM fit object over here, and then the contrast matrix from over here. And that's how I run the eBay. So you have to do the LM fit, then you do the contrast fit on the LM fit object using the contrast matrix that you made. And then, okay, all of these results are bogus because it's not an actual protein. You're not going to get anything out of here. But it just shows, this is kind of what I wanted to tell you. So over here, when you do top table, you can very easily select day 14 versus day 7. And that selection at coefficient will give you the genes that are differentially expressed between day 14 versus day 7. And then easily like that, you can pull out day 7 and day 0 or 14 or day 0, exactly how you would want it. And then this is a very handy function that only works with make contrast, which is the decide tests. So you use the decide test and put in your actual your matrix, which has Bayesian statistics applied to it for the contrast matrix that you have. And again, you just put in the adjust method, FDR, p-value, whatever you want. And this gives you a very handy table of how many differentially expressed genes are upregulated versus downregulated at these different time points. And you can see nothing is significant because, of course, again, it's not a real protein. But when you do it with your actual data where you do have time points, it'll very clearly show you that the number of genes that are upregulated versus downregulated at these different time points. This example was just to run through again how this contrast fit function works. Okay. Any questions till now? Yes.
We were just comparing COVID yes and COVID no, which when COVID yes versus COVID no, or COVID no versus COVID no, I mean the whole change was
So yes, that was COVID, yes.
COVID yes.
Yes, yeah. Again, yeah, you have to be very specific and careful about the direction that you're choosing it to be in. Like, are you taking like, is your relative based COVID yes, or is your relative based COVID no? So that's why the model matrix explicitly changes it to it's COVID yes, which means that the baseline is if you like patients having COVID. Yeah.
And where did you just show that?
Sorry,
I mean, where did we show the baseline?
whether we select the baseline. So you can very explicitly again say that it's COVID yes or no, but in the model matrix, if you saw, okay, let me find that over here. So it automatically gave it as COVID yes. So it recoded the column by itself. Okay. Yeah, if that, so the one is like, yeah, that's the base, and then the other one is the one we're comparing to. Okay, so then we're done with this example. And now we're heading towards enrichment analysis. Now this all should work. But sometimes like if it doesn't, then you should have all of the objects saved within the data folder. All of these over here. And if that doesn't, like, don't worry, it's all in the completed script. So hopefully when we run it, now it'll work. So there's quite a few comments that I've made in the actual script, but I'm only going to be typing in the functions that we'll use. So we're going to use this package called as biomart, and the mart object is the one that specifies which data set within this biomart package which data set or which organism within this data set to use. So we're using the Homo sapiens database because our samples are human samples. And so I will explicitly tell it to, I'll use the use ensemble. You can also use a use mart function, but I've noticed that the use ensemble actually works much better. And then from within the ensemble database, I want the sapiens gene ensemble. If that takes way too long to load, I'm just going to go over here at the end and copy this. Okay, that worked. But if that doesn't work, you should have an object loaded and called as HASmart within your data. So here we go. And you can just load that in as a R object. It'll look exactly like what this mart object should look like. It's quite big, 1.4 MB. And yeah, that's what it looks like. It contains all of the information that you would need, to generate any type of like expression enrichment analysis that you would want. So I'm just going to comment that out. And then I'm going to I think we're going to use the lactate model just for this example, because that one did show us that lactate does indeed contribute towards the model. So I'm going to select the top 10 genes. So just exactly the same command I ran. All of the genes, so n infinity, and then get the genes as row names. So these over here, you will see all of the genes that were significant for this specific model at a p-value of 0.05. And I'm going to subset that further in to only include the top, I think just the 100, because 1 or 200, I think 200 is fine, because Biomart only likes to take in queries up to, I think, 500 entries, and if you do more than that, it crashes and it doesn't load. So I'm only going to select the top 200 to run this. So I changed from genes like 5,000 to 200. And when we're actually running Biomart, there's a lot of attributes or filters you can apply to get the information that you want. So what we're going to do is we're going to convert our gene names to actually entree IDs, because entree IDs, ensemble gene IDs, all of these IDs are used for very specific functions. One won't work for the other. So when you're working with genomic data, unfortunately, this is something that you'll have to do a lot, like converting between different gene IDs. And so just for that, I'm going to, and if you just put in like, if you use these two functions here, the filters list attributes smart, list filters and list attributes, it gives you a whole list of all of the filters and attributes that you can use. So like I mentioned here, filters are the parameters that you search by. So over here, it will be our Hugo gene IDs, so 8 GNC IDs. The attributes are the matching parameters that you're wanting to search for. So it'll be your actual entree IDs that we want. So let's see, I'll explain what this means here. So I'm going to name the object at GNC to entree. The function is called getBM. Now our attributes that we want to return from our query are the GNC symbol, because if we just include entree gene ID, then we don't know what that gene name corresponds for. So you always have to put in the attribute, the filter that you're searching for by in the attribute section. The filter is the GNC symbol because that's what we've been using. So that's the gene name. Values are the genes, so these 200 genes here. The MART specifies the MART over here, so the Homo sapiens data set. If I run that, that might also take a while. Oh, okay, it didn't. And this is what we get. And this is, again, I would just really recommend, like when you're starting off with any sort of gene analysis, just get a data frame of all of your genes converted into your different IDs, because you will use it at some point later on. It will take a lot of time to run, but when you have that, it's just so much easier to go into as a text file and then just write join or like just pull out the ones that you want instead of doing the Biomart getBM function over and over again. Okay, so we got that. And then because the reason is that sometimes some parameters are only searchable by certain IDs. So in this case, we're going to search for some Go terms. Again, a caveat with Go terms is that I don't actually like using them because I don't think they give a good representation of what that gene really means. But it's something that everyone asks for in publications. And so it's just a standard step, just do it. But please don't attach any weight. Don't attach much weight to the results that you get. Okay, so again, I'm just going to copy paste from here because that's made my life a lot easier. So I'll explain again what I mean. Again, if it doesn't work, there should be a Go terms RDS over here in your data folder. So I'm going to call the object Go terms, use the getBM, the attributes or things I'm searching for, the GNC symbol, the Go ID, the name 1006, which is, again, if you go into over here, and if I run list attributes, I get this data frame, which tells me exactly what the definition and what parameter I'm going for. Name 1006 is the Go term. I don't know why they've named it like that, but it returns the Go term over here. And then definition is definition 1006 is the Go term definition. So those are the things we want to pull for. Namespace is the Go domain. And so the filters again are a GNC symbol. Values are genes, smart is smart. Run that. Because we have a lot of attributes listed, it takes a little while. So we got that now, and this is how it looks like. So for each single gene, we have these many Go IDs, and these are the definitions that you have. So you can see, like, it's not just like one gene per one Go term that you get a lot of them. And that's why, like, I don't think Go definitions really give you much about what the gene, like specifically what the gene is doing. Okay, so there are a few empty rows which you will come across at some point. So I can't find them right now, but yeah, here you go. So there's just no Go term for this, and but it still fills in. So we're going to remove those. So I'm just going to put them as empty, and then I am going to, because it was not coded as an empty cell, and to select that empty cell, I have to actually put in an NA so that I can use the NA omit command to remove that. So you see now the empty cell will be labeled as an NA. So now that gives us a much easier way of removing these empty entries. I just do that. And then I'm going to count the frequency of each of the Go terms. So protein binding of our 200 genes, and with the multiple Go terms, protein binding is the Go term that came up the most, 171 times. And then the rest of them I've arranged by frequency. So count by name 006, arrange, meaning you will want to arrange the column sequentially, but I want it by descending, so I have to specify descending, and then N is just the name of the column here. And so we're just going to run this to make a plot to see how our Go terms just like visually depict the frequency of our Go terms, basically. So Go plot total, I'll just put in total as a column over here because those are the number of genes that we measured. I'm going to get the percentage of that Go ID within the results that we got. And then for the first 20 plots, I'm going to make a plot. So this is not how we want it to look like. And then so there's quite a few arguments I've applied here. So it's just reorder name 1006 by the percentage column. So we want to go from descending the highest percentage to a slowest percentage. Y-axis is the percentage. And then I've changed the y-axis over here. I have adjusted the text so that the text on the x-axis is not horizontal, but at an angle of 45 degrees, and moved just a little lower by using the HJust argument. And so when you do that, this is what you get. So, so it just shows us basically what was in table form in a visual form. So visualization, like having a graph, is much more intuitive than actually having a table in general sense. And when you're presenting, it's always nice to have a graph. So I'm also going to add the namespace 1003, so which was the cellular compartment, and then I'm going to just join it. So this is what we had in the namespace. So it's molecular, cellular, or biological. There's only 3 components that they give for these Go terms. And then over here, I've just specified that I want the figure height to be 4, the width to be 4. I'm calling it Go plot. I'm just having the top 20 terms. Ew. Okay. Yeah, so this is kind of what you get like. So this was just a few basic steps to show how you can better your plots and just display them according to however you would want. Again, be very careful of using code terms. And then this is the last step. So 140, we're doing good. And I'm going to, so I'm pretty sure you must have heard about the KEGG consortium. So it is a curated database of just gene pathway interactions. I trust KEGG a lot more than I do Go terms. And so what I will do is for the 200 genes that we have, I'm just going to pull out some results and see what we basically get. So I'm going to load in the cluster profiler package. And this is just to see what we have over here. So our agency symbols and then our entree IDs. Now KEGG only takes in the entree ID. So that's what I meant. So in this case, if you submit by agency, which you will see in the script over here, if I go right at the bottom, I run the same thing, but with just the genes. So just our gene names over here, it doesn't return anything. It runs, but it doesn't work. And it took me a while to figure that out as well, because it would not give me any actual error. So in that case, that's why I had like the previous steps to convert it into entree IDs already. So that's what we're going to do. So we use the function called enrich KEGG. The gene is our agency to entree ID data frame, but our actual entree IDs, and our organism as our human Homo sapiens. And when I do that, again, when you're submitting these queries, try to put in as minimal as possible because it does take a lot of computation to run. Yeah, it might hang sometimes. Okay, so and the way you pull that out, so if you open KEGG, sorry, this is what you see. So this is the result column right here. And it gives you a lot more information than we had before. And just a way to save it is just KEGG res result and then KEGG. So this is pretty neat. And you can look at the description of all of these different columns online. It's quite comprehensive. And given that KEGG is a curated database, you know that you're not really going wrong. And then the results that you're getting, like your Go IDs, like multiple Go IDs to one gene, is not going to be happening because this is thoroughly looked after. And yeah, because I was able to copy paste, we are ahead of time. And so I'm open to any questions now. Okay. Looks like there's no questions. Yes.
Actually, it's a very basic question.
Uh-huh.
When you do these commands where it's like the name and then the arrow and then the same name, where you're adding to itself.
Yes,
If you run it more than once, does it append more than once?
it does. So the number, if I have like PDAT, dash PDAT,
Yeah.
the first one will replace, like, it will replace the first time. If you run it again with any more additions, it will replace that one as well. So it's an additive effect. Some
code again.
Yes, if you're replacing it, that's where I was like, make separate data frames, because if I've already replaced that and you run some code from before, it might not have those columns that you're looking for because we've already run before, right? Does that make sense? Yeah.
But when you were saving the results, why did you do that?
Oh, yes. Okay, that's a good thing. So sometimes the dollar symbol works, but in this case, I tried to do the dollar symbol, but it wouldn't give me. So let's see. Okay, I'll just share this again. So if I try to do KEGG dollar, KEGG and dollar. You'll see that nothing's coming up because usually you'll just put in something and tab, it'll come up. I think it's the way that the data frame is made. So KEGG, it's a enriched result. So it's not a data frame. It's not a typical structure. So in this case, when I do want to access it and when I wanted to take this result, what I did is just click this arrow over here. And in the console over here, you'll see that it's an @ result. So someone who has more experience with this type of object, feel free to speak up, but sometimes you need to use the @ to pull it out.
Yeah, Nikita, maybe I can add a little bit to that. Just, there you can see next to the definition of the KEGG object that it says it is an S4 object. And so my understanding is that S4 is like a structure of object that many other packages reuse and kind of put more features into it. So for example, this one's based on S4 object. And so for accessing the slots of those objects, you always access them with the @ symbol. That's in contrast to lists where you access them with the dollar symbol. And remember that data frame is sort of a type of list. So that's why you access data frames with the symbol, the dollar symbol as well.
So would you then subset out of like gene sets, which is a list of 173, would you @ result dollar gene symbol?
Let's see. If I do that, it's @ gene sets as well.
Oh.
Yeah.
But if you were to try and pull an individual item from the huge span of gene sets.
Gene sets is a list. So for there, you would use the dollar symbol after the line that Nikita has in her. Exactly. There you use because that's a list. But the KEGG is an object, is an S4 object.
Yeah.
And gene sets is a list.
@
Yeah.
dollar, so that you're isolating an object or a list from the larger object.
Mhm.
If you want something out of
The list, you do the opposite. Yeah. Sometimes you also use the double square brackets when it comes to lists to index the list that you want, the elements that you want to select. Within that, you can also index it further. So it just really depends on the data type that you have. Each single data type has its own ways of pulling out the data or working with the data. Lists are, I find, quite difficult to work with when pulling stuff out. Okay. Thanks, Alejandro. That was a really good explanation. Okay, any more questions? Okay, if not, I'm just going to share. Yes.
So what general advice do you have for those of us trying to start learning this stuff that feel kind of lost?
Yes. Okay. I would say there are quite a few tutorials online. You just need to go and find them. There's several bioconductor packages have their own tutorials. There's the Harvard Chan Institute, EMBL EBI. They have, and every single one uses its own parameters of filtering, normalization, all the steps that they apply. So what I've done is literally go through all the ones I could find and the ones that I really liked and made sense, put them together in a way that benefited my workflow. So basically what you see over here is a culmination of a lot of different articles, a lot of different tutorials all together into one that made sense to me. But obviously something might be better for you, so you might change that. Just literally just Google. There's like a lot of stuff online. Yeah.
This is also incredibly helpful.
I'm glad. Okay, I just have a feedback form for everyone to share. This is specific for every workshop lead. So this is in particular for this workshop. And I will just open this up. Okay. Okay.
Also put it on slide.
Okay, yeah, that's the feedback form for this particular workshop. And yes, so if you have any questions, I'm just typing my email in the chat.